great honour to be here at your retirement do. I'm going to do something slightly different from what Paul did. Paul gave a fantastic summary of your career and your achievements. What I'm going to do is give a couple of anecdotes to show how your work and your influence on me has influenced what we have done and has confirmed everything that you thought about. So the first time I interacted with Redgrave, I think, was at a IBRO World Congress Symposium in Montreal. I can't remember what year it was. Actually, it was about 1991, I think. I didn't know him very much, but he was very characteristic with his check shirt, this pocket stuffed full of stuff, and elastic band usually, because it was so stuffed that the button wouldn't close. You had an elastic band round to keep it closed. You stopped doing that now. Anyway, so I was talking to him, I think, at his poster, and he said, "Oh, I was really interested in your poster." And I said, "Oh, well, we talked about it. I said, well, I can let you have the information." He said, "Doesn't matter. I've already taken it down off the board, photocopied it, and I've got it here." He refers to that as when he stole my results. Now, I went back and checked what abstracts I had at that symposium, and it was these, and I suspect it was this one that he was interested in, and that was the input from the thalamus into the striatum, subcortical inputs into the basal ganglia. And that's been one of his threads of his research, and many discussions I've had with him about subcortical connections with the basal ganglia. The basal ganglia, I think Pete says, was hijacked by the cortex. I think that they put it all together. They put it all together in one of these reviews here. So here we have cortex, striatum going to the basal ganglia output nuclei, then to the thalamus, and then back to the cortex. But Pete really showed that and really pushed the fact that there were subcortical inputs to the thalamus. Thalamus was projected to striatum, and then to the output nuclei and back to the cortex. So a lot of my work has been on these connections. And I think people would agree that many times, actually I have difficulty editing this slide to make it look neat, but many times big chiefs giving lectures on the basal ganglia will only consider the thalamus as a target of the output of the basal ganglia and then projecting back to the cortex. So of course we know that this is the case, that the thalamus is innervating. This is simplified again. The thalamus is providing a massive innervation of striatum, which I'll get to in a moment, subthalamic nucleus, and probably other regions of the basal ganglia as well. It arises principally from the intralaminar thalamic nuclei, but also most of the other nuclei of the thalamus innervating the striatum. What does it do? We know that the thalamus is important in many things, but probably most important for Pete's stuff is it's carrying the information that's coming is salient sensory information coming through thalamus and then getting into the striatum, helping in action selection, I would guess. And also we're quite interested in the innervation of the cholinergic interneurons, which I'll talk about a little bit later on, and that there may be interactions with a cortical input and gating a cortical input. So there have been many studies, starting in 1971 on the connections of the thalamus with the striatum. This was done in Oxford by Tom Powell in the 70s, and again, this is completely ignored. But this slide here is taken from Yolande Smith's work, and it shows the principal targets in the striatum of the corticostriatal projection and the thalamostriatal projection. So this is the input from the motor cortex, going principally onto spines. It's going onto the spines of these neurons, and these are the principal neurons of the striatum, the output neurons of the striatum. They're the equivalent of the pyramidal cells in cortex or Purkinje cells in cerebellum. So motor cortex is doing that, all cortical regions do that, onto the spines of these cells. And then Yolande very carefully was injecting many different regions of thalamus and showed that mostly they're going onto spines, except for the parafascicular nucleus, which is going principally onto dendritic shafts. And actually it turns out that we know that is because they're innervating cholinergic interneurons. The field sort of was transformed when we got molecular markers of the cortical projection and the thalamic projection. And the molecular markers are the vesicular glutamate transporters. So both pathways are using glutamate as a transmitter, but they use different isoforms of the transporter which puts the glutamate into vesicles. So we know that the cortical projection uses vesicular glutamate transporter 1, and the thalamic projection uses vesicular glutamate transporter 2. So we get antibodies against these two transporters, and we can do some really neat and geeky quantitative anatomy of these projections. And what we found, ourselves found and several other people have found, is that actually, as a proportion of the synapses in the striatum, the thalamus provides a similar number to that coming from the cortex. So the subcortical input coming from the thalamus, in the terms of the number of synapses, is equal to that of the cortical input. So ourselves did this, Yolande Smith and some other groups. And we use these markers to look at the synaptic organization of the cortical and the thalamic input. We actually took advantage of some of these green fluorescent animals which express GFP under different promoters, so we could identify the two different pathways coming from the striatum, the two types of these spiny neurons, those that give rise to the so-called direct pathway and those that give rise to the indirect pathway. And by using those mice together with these molecular markers, we were able to demonstrate that direct pathway neurons coming down here are receiving input from the cortex, so this is V-loop 1, and also receiving input from the thalamus, that's V-loop 2, and similar proportions of those synapses going onto those neurons were from the cortex and the thalamus, that's the direct pathway neurons, and similar to the indirect pathway neurons, that's those neurons giving rise to this projection. Because up until this time, there was some idea that there was a segregation between the two pathways. So both direct pathway neurons receive cortical input and thalamic input, indirect pathway neurons are receiving cortical input and thalamic input. And then some work done by Cornelia Herto-Ocampo in the lab where she recorded from neurons and labeled them in a slice and then did histological analysis of individual neurons. She was able to demonstrate that individual direct pathway neurons and individual indirect pathway neurons are receiving both cortical and thalamic input to similar degrees. So here's a spine of a direct pathway neuron receiving input from the cortex, and here's the spine of a direct pathway neuron again receiving input from the thalamus. So what about central to what we understand about basal ganglia is the interaction of the dopaminergic input coming from the substantia nigra with the cortical input. And the dogma in the field is that the dopamine innervation of the striatum principally goes onto spines, that's the spines of these neurons, and the effect of dopamine is to modulate the response of this spine to the excitatory input coming from the cortex. So glutamate is released here, this spine is responding to it, and then dopamine released here is modulating the response of that spine to the cortical excitatory input, brought about by a whole variety of mechanisms. Actually, and John here has done quite a lot of the work on that. What about the thalamus, and does it do the same? So we did a similar study and we looked at the thalamic input. And we looked at the cortical input, and it turns out that the glutamatergic input from the thalamus going onto a spine here, here's the spine, and here's the dopamine terminal sitting here. It turns out that the relationship between dopaminergic input and the cortical terminals and the dopamine input and the thalamic terminals is exactly the same. It's about 20% of those spines that are receiving cortical or thalamic input of this dopamine terminal sitting on here. This was the most geeky electron microscopic analysis we ever did, and thank goodness I had students who were happy to do it. And we got some really interesting data about the innervation of the striatum, which I'm not going to go into now. So it turns out that the thalamic input actually is highly heterogeneous. It's coming from different subnuclei, and the different subnuclei, the neurons have different properties, morphological and electrophysiological properties. This was work done by Carolyn Lacey, who was a student in the lab, and she was recording from the rostral intralaminar thalamic nuclei, probably the central atrium, and following the recording, she would fill the neuron, and then would look at the morphology of the neuron, and then look at the connections of the neuron. And she'd also do it in the caudal intralaminar thalamic nuclei, that's the parafascicular nucleus, and this is always been one of my favorite slides since 2007. So this is the recordings from one animal, 2 electrode tracks, one there and one there. This is a parafascicular neuron that she recorded from, and this is a neuron in the central lateral nucleus that she recorded from. And you can see that these neurons have completely different morphologies. This is very reticular appearance, and this is very, very bushy and very typical of a thalamic neuron. Different electrophysiological properties. So this parafascicular neuron produces these bundles of action potentials which are associated with what's going on in the cortex. The centrolateral neurons produce very typical thalamic response, so these very high frequency bursts of action potential. So this is not one action potential expanded here, there's very high frequency bursts. And then when you looked at the synaptic connections of those same neurons in the striatum, turns out that the axons coming from the parafascicular nucleus, 80% of them are onto dendritic shafts, as we knew actually from before, and these dendritic shafts are probably the cholinergic interneurons in the striatum. 20% actually were onto spines. And actually this average here belies a really complex heterogeneity there, because some of those neurons exclusively innervated spines and some exclusively innervated dendrites. In contrast, the rostral interlaminar nuclei, and probably all the other thalamic nuclei that are innervating striatum, just went onto spine heads like this, just like the cortical input. And we're taking this a little bit further forward by looking at the properties of this synapse and those synapses from the parafascicular nucleus which are going onto spines. Do they have different properties, the actual synapses? The way we did this was work done by Thomas Ellender in the lab. He was a postdoc at the time. We used an optogenetic approach. And actually this was, I think, the first or second paper in the UK using optogenetics in mammals. There's lots of stuff in those funny little creatures, but in mammals. So we put channel rhodopsin in different parts of the thalamus, the rostral thalamus and the caudal thalamus, the interlaminar thalamus, took slices of striatum, recorded from spiny neurons, shone a light on them and got activation of those synapses. But it turns out that they're completely different properties, so that the size of the response was always, let me get this right, always greater for one of them, I can't remember what it was now. For paired pulse facilitation for the centrolateral, and paired pulse depression for the parafascicular synapses, the NMDA AMPA ratio was far greater for the parafascicular nucleus than the centrolateral nucleus, and you could get LTD at the parafascicular synapses, but not at other synapses. So we concluded from this one that the parafascicular input to the spiny neurons is ideally suited to modulate the response of that neuron to other inputs, whereas the centrolateral input, and probably other thalamic input, is designed, like the cortical input, to get that neuron up to firing state into its depolarized state to fire action potentials. So the thalamus is not only a target of the basal ganglia, it provides a massive input to the basal ganglia. It's highly complex and highly heterogeneous. I think we're probably only just scratching the surface about the heterogeneity. I sometimes say that unlike the cortex is heterogeneous, but actually we don't know. The cortex may be as complex and as heterogeneous in its input to spiny neurons as the thalamus is. So yes, P. Subcortical inputs to the basal ganglia are dead important. Okay, I want to turn to another subcortical input to the basal ganglia, just give you a few slides and just scratch the surface, go through them quite quickly. So quite a bit of it is unpublished. So we have this classic view of the basal ganglia. This is the basal ganglia in here, direct pathway, indirect pathway, cortex, thalamus, output, either to thalamus, back to cortex, motor region, or to these subcortical structures involved in behavior and movement. Because I want to concentrate on this for a moment, and it's nothing like this. It's more like this, that there's this, the pedunculopontine nucleus and the lateral-dorsal tegmental region in the brainstem feed back massively onto the basal ganglia, in many regions of the basal ganglia. And one of the slides I'll show you later actually is that there's actually a very prominent input back to the striatum, which is innervating spiny neurons in the striatum. I think we're going to hear, as Phil Wynn's around somewhere, I think we're going to hear about the pedunculopontine later on, but I'll just very briefly mention a few things. One time considered to be a cholinergic nucleus, because it's packed with cholinergic neurons. In fact, there are many types of neurons there, including glutamatergic neurons and GABAergic neurons, and it might be, in fact, that cholinergic neurons are the minority. Only about 20% of the neurons are cholinergic, whereas 40% are glutamatergic or GABAergic. But many of us are interested in the cholinergic neurons, and they can do some remarkable things. So, similar sort of experiment as I showed you a moment ago, we're recording from a neuron and then filling the neuron at the end of the recording. We showed that the individual cholinergic neurons in the pedunculopontine nucleus can actually innervate every structure that the PPN is known to innervate. So, and different subtypes have different electrophysiological properties. So what we have here is, in black, the cell body and dendrites of a cholinergic neuron. We know it's cholinergic because we did all the immunocytochemistry after the electrophysiological recording. And this is its axon in red, and it's innervating all the regions that are on the list that the PPN connects to. Just skip over that. So again, we have fantastic tools now that we can study these things in detail. This is the chat Cree rats. So they have, it's one of these genetic, what does Ed Stern, who works in the basal ganglia, calls it black magic. It's all black magic to me. So you can inject into this animal a viral vector which will only be expressed in cholinergic neurons, and the vector we use is something which will enable the cell to express a fluorescent protein and channel rhodopsin. So we inject different regions of the pedunculopontine nucleus with these viral vectors. And in fact, we see a massive innervation of the striatum. And this is a study which done by Juan Mena Segovia and Daniel Dotan in the lab, and they're looking here at the input from different parts of the pedunculopontine nucleus, the rostral, the caudal, and the lateral dorsal tegmental area, and the innervation of dopamine neurons in the midbrain and the ventral tegmental area principally, where they're making synapses that have different patterns of innervations, different density of innervations, different electrophysiological properties of those connections. Shows, in this case, so here they're recording from a neuron. That's the marker they put into it. They know it's a dopamine neuron because it shows tyrosine hydroxylase positive. They turn on the laser and then you can see an increase in firing of that neuron when they activate that cholinergic input coming from the brainstem. They've also been looking at the input to the thalamus. So a whole series of injections in different parts of the brainstem, mapping the input at the level of the thalamus. And this is work that's really in progress at the moment. And it seems that there's a functional topography of that projection relating to the functional topography of the brainstem and the different thalamic nuclei. But this is the one that I love the most, and this is the striatum. So this is striatum from an injection of the viral vector in the pedunculopontine nucleus. So we're looking here in the striatum at the green fluorescent protein expressed by those cholinergic neurons in the brainstem. And there's this massive innervation of striatum, cholinergic innervation of striatum coming from the pedunculopontine nucleus. It was a complete surprise to me because for decades we've been saying that the only cholinergic innervation of striatum is coming from the cholinergic interneurons. And this has a tight topography as well, depending on where you inject. This part of it has actually been published. And then Daniel and Juan have been recording from the spiny neurons and then looking at the effect of activation of those different projections. So it seems that the different parts of the activation of synapses, cholinergic synapses, coming from different parts of the pedunculopontine nucleus are producing a depression of the firing of spiny neurons. This is in its early stage and not finished yet. So, subcortical inputs to the basal ganglia are really important. I'm not going to talk about any more science now. I'm going to talk about some anecdotes about Redgrave. So Pete and I were invited, both invited to Movement Disorder Society. Actually, it was a society which Jose Obeso is heavily involved in, unfortunately is not here. It's a clinical meeting, and I was slightly stressed going, you go to a clinical meeting, everybody's going to be really smart in suits and ties. And I was going by train from St Pancras, and I forgot my tie. I brought my suit, as you can see. It's the only time I've ever given a lecture in a suit. And so in Marks and Spencer's, at St Pancras station, I bought a tie, and you can see that beautiful tie, wearing a tie, giving a lecture. That evening we were having dinner with Pete Redgrave and actually Yolande Smith. I can remember it was a really nice French restaurant, and I had the most awful choice of food. I chose cow's kidney, and you play cake with this great thing, knobbly thing, with a bit of gravy around it. Anyway, so Redgrave was talking about, he's slightly stressed, there you were wearing a tie, Paul, in the meeting, and I've been looking around the Palais de Congrès and to try and buy a tie. They're all about 90 euros. It's ridiculous. Don't worry, you can wear my tie. Here it is. I'm really dapper. There's the time. There's the time. He's not looking He had his jacket on as well, and he didn't roll up the sleeves of his jacket during the talk, as his tendency to do so. Okay, same pictures I think as Paul had from Google Image. Now I'm going to get to my notes. So this is the part where it's like a memorial service. People to say nice things about it. So the first thing that comes to mind is cheap date. He's completely content with a orange juice or a Diet Coke. No, not a Diet Coke. You always have the ordinary Coke. So he's a cheap date. Other things, great scientist. I think he's a great scientist. Pete really, really tries to understand what the brain's doing and how it does it. And I always feel slightly, I should be a better scientist. I should try and do these things. And I really understand how the brain works, not just do boring connections and synapses and physiology. I think he's a psychologist who appreciates structure of the brain. He doesn't consider the brain as a black box. I think black box would never be in your ideas. He's a great conference buddy. It's great to be at a conference with. I think you were alluding to it, Paul. Stimulating discussion, challenging discussion, science, really challenging. And he always spends a lot of time with young people and is always ready to listen to them. And I think all in all, he's a jolly good chap. That's what I would say. Some expressions, one of the expressions which sticks with me is glam-max. I always refer to nature, neuroscience, and nature and science as the glam-max, because that came from Redgrave. So okay, I'll finish there and just thank those people who did the work. So Natalie Doig, who did a lot of electron microscopy, so did John. Ignalia did electron microscopy as well. Caroline did those thalamic neurons and worked closely with Pete McGill the whole time. And Juan and Daniel did the PPN work. 2 more points. Natalie, thanks for saving Natalie's life, which... and number 2, Pete sends you a big kiss. Thank you.